I think we can start now. Uh, um, so second class, yeah, and we're doing geometric trig today. Okay, so geometric trig is trigonometry in triangles. So introduction. So before we did trigonometry in the unit circle, now it's gonna appear in triangles. They're mainly in right triangles, but there's other applications in acute and obtuse triangles, including law of cosines and law of sines. Many properties can be proven using triangles. In geometry, trig is also used for some solutions, like bashing out everything you know. The purpose of this chapter is to introduce how trig is used inside primarily triangles. So I don't have a good image, so I had to hand draw stuff. So sorry about that. Um, so right triangle trig, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Other trig functions are based off these three, and you can also find the height of the triangle with this very bad diagram, but I think you can read that. Um, you can also get identities like cosine squared plus sine squared is one. Yeah. In the following diagram, okay. So here's one problem. So in the using right triangle trig, can you find sine alpha? Uh, if you get the answer, you can DM it to me on Zoom. I'll give you all like another minute. Actually, this is not too trivial for a first problem, so I will give you a hint. When you're trying to find the sine of something, you want the opposite and the hypotenuse. And and those are side lengths. So you do want to bash out the side lengths here, but it's not that hard of a calculation. Okay, I'll just go ahead and explain this because it's kind of hard. Uh okay, so sine alpha. By the angle bisector theorem, I think this is worth knowing. Let's say this is oh shiny annotate. This is D. Why say yellow? Let me pick a better color. Here. So let's say this is D, right? Then by the angle bisector theorem, BD over CD is equal to AB over AC, which is equal to 7 over 25. If you do some basic calculation, you'll get that BD is equal to 721 over 4. All right. We know that AB is equal to 7, so therefore we know that AD is equal to 35 over 7. Or wait, no, 35 over 4. So BD over AD or sine alpha is BD over AD, which is equal to 21 over 35 or 3 over 5. Right. Next problem. Let's see. Oh, shoot, where's my bed? Uh, give me a second. Okay. Go back. Okay. Next problem. Okay, in triangle AB, actually, I can draw this out for you if you want. AB is 4, A 4, AC is 7, and this angle is 60 degrees. Find the area of ABC. Also, try to do this with only things that try to do this with only things that I've shown you this far, which is like 10 minutes. But I'll give you all like 2 more minutes because um I didn't show this in depth yet, so my bad. Oh, it's been another 2 minutes. I'll go ahead and show this. Oh, okay. Um, I'll go ahead and show this. So if you have 4, 7, and 60, then okay, let me label this. And okay, so the height, we know the height is gonna be 4 times sine 60 because this height h over 4 is equal to sine 60. We know sine 60 is root 3 over 2. So the height is 2 root 3. So the area is base times height over 2, which is 7 root 3. All right. Um, yeah, it's that simple. Also, okay. Next. Law of sines. So in a triangle, uh, so this is extended law of sines. The short one is just the first three. A over sine A is equal to B over sine B is equal to C over sine C, which is equal to 2R. R is gonna be circumradius. R is gonna be circumradius. Okay, also, so circumradius is like if you have a triangle ABC, right? Oh God, okay. Uh, so if you have a triangle ABC, circumradius is gonna be the center of the circle that includes all 3 points, and the radius is gonna be the radius of that circle. Um, can anyone prove this formula? Uh, does anyone want to try? Also, if you want to DM me, DM my computer. Okay, I guess I'll just show how to do this. It's not that simple. Okay. Uh, so in your triangle, let's say this is A, B, C. And let me get a thinner line. Okay. So this is the height, right? H. H, as we know from like the second slide or something, H is equal to AB sine angle ABC. It's also equal to AC sine angle ACB. From our naming conventions, AB is C, the letter C, and AC is the letter B. So then we know C over sine ACB or C over sine C is equal to okay actually let me write this out. Uh, all right. So C over sine ACB or C over sine C is equal to B over sine ABC or B over sine B. And if you want to do it for the other ones, you just draw the other height. Um, yeah, okay, and then I'll prove the 2R part as well. Uh, okay, let's see. So if we have a triangle and we have its circumcenter A, B, C. So 2 times its circumradius is just the circle's diameter, but we'll ignore that for now. Because if we draw OB and OC, we get an isosceles triangle, right? Because the circumcenter, um, it's the center of the circle containing all 3 points. Um, if a circle has 2 points on it, the 2 points are equidistant to the center of the circle. So this is R. The angle from the center is also equal to twice of this angle. So so this small angle is equal to angle A because the whole thing is 2 of angle A. So R is equal to, so this is R, this is A over 2, yeah, this little segment here. And this is angle A. So R is equal to, well, actually, let me not do that. Sine angle A is equal to A over 2 over R. So R is equal to R is equal to A over sine angle A and is thus equal to all of these. Yeah, that's a quick proof. Okay, next slide. Okay, so this is an example. I'll give you 3 minutes to do this. Okay. I'll give you all 3 more minutes to solve this. If you get the answer, send it to my computer. Okay, I got more responses, so I'm actually just gonna start explaining. Um, triangle ABC, AB is 5, ACB is 30, ACB is 30, and ABC is 45. Oh, my drawing is so bad. Okay, what is AC? Okay, well, we know AC over sine 45 is equal to AB over sine 30. AB is 5. So AC is equal to sine 45 over sine 30 times 5, which is equal to root 2 over 2 over 1/2 times 5, which is root 2 times 5, or 5 root 2. Alright. Yeah. Next problem. Okay. Yeah, for this one, you're just finding everything. Wait, let me use this one. This one solve for like just everything that is unknown. You can use a calculator because the angles are not nice. I'll give you all like 3 minutes to do this. Also, please round to two decimal places. I think that's good. Okay, this one I'll give a bit more time actually because we are not in a rush. I'll give you like 2 more minutes. All right, I'll go ahead and solve this. Okay, so we have this side length, which is across from this angle. So that's probably gonna be our pair. 10 over sine 30 equal, equals C over sine 125. We know alpha is 180 minus 125 minus 30, which is 25. So it's also equal to A over sine 25. Sine 30 is 1/2, so this is 20. A is equal to 20 sine 25. C is equal to 20 sine 125. Mm, you should know how to use your calculator to do trig stuff. You'll get A is equal to 8.45 and C is equal to 16.38. Next problem. In triangle PQR, we have PQ is 5, angle PRQ is 60. What is the circumradius of PQ? I'm gonna solve it now because it's been a while. Okay. PQ is 5. PQ is 5. Okay, that's great. PQ is angle PRQ is 60. What is the circumradius? So you could use the formula. 2R is equal to 5 over sine 60. R is equal to 5 over root 3. Um, while that is a valid solution, I think I should still show how to do this without using the formula. So, okay, let me erase this part. So if we draw P, Q, and R, and we also draw circumcenter, we will get the 60, so it's 5. So this angle is 60, which means, and okay, so angle let's label PR's midpoint as M. Angle POM is equal to 60 degrees, and PM is equal to 5 over 2. And with our basic trig, we know that OP is equal to 5 over 2 over sine 60, which is equal to 5 over 3. So that's also an approach you can do without the formula. Alright, now I'll let Samuel talk. Should I turn you into host?
Yeah, sure. That's fine if you want.
Okay. Um, give me a sec. Let me stop sharing first, so that I can. Okay.
Yeah, okay, thank you. Okay, so yeah, so this next question behind is a application word problem of law of sines. So the let's see. Okay. So the question says that we have place right over place A is located 150 miles due south of station B, which is over here. And then a ship at sea, which is right over here, sent an SOS call that is received. And then they were able to detect that the angle over here is 60 degrees and the angle here is 55 degrees. So what this right here means, if you aren't familiar with how a compass on a map works, is that so how to read something like n 55 degrees east is that you simply start, n means north, so we start north and then we turn 55 degrees east. That is all this is saying. For example, if it said south 12 degrees west, then it would look like this. So in this case here, from station A, the ship is located 55 degrees east after facing north. So it will be 55 degrees from north direction. And then for station B, it's 60 degrees from straight south. Okay, I'll erase this real quick. Okay, so we want to know how far each station is from the ship. Basically, we want to solve this triangle. So the first step will be, of course, to find this angle over here. So we use 180 minus 55 minus 60, which is 65 degrees. And then we use law of sines. So we have, let's call the ship S. So this right here would be B. This right here would be A. So AS over sine of 60 degrees is equal to BS over sine of 55 degrees, which is equal to 150 over the sine of 65 degrees. So then we can compute AS is equal to 150 sine of 60 degrees over sine of 65 degrees. And BS is equal to 150 sine of 55 degrees over sine of 65 degrees. So because I don't have a calculator, I would just write what I have. So like if you were to do this yourself, you would like plug this into a calculator. Different calculators have like different settings and whatnot. And I believe that if you're taking a rigorous pre-calc course, your teacher would just go over this. And it shouldn't be too hard to use anyway. So I think this right here turns out to be 143.33. And this right here turns out to be 135.57. In AP pre-calc, you would typically want to round to 3 significant digits. I will not do that here because I don't have that. And I also don't want to plug it in. So into a calculator. So yeah. And question B says that if a helicopter capable of flying 200 miles per hour is dispatched from the station nearest the ship, how long will it take to reach the ship? So essentially, it's saying what is the closest, what is this height? So because we want the distance from the shore that is, let me see. Oh wait, I think, wait, no, it wants to find the distance. It wants to consider which of A and B is closer. It's really clear that B is closer. If you just look at your values here, and wants to ask if a helicopter flying 200 miles per hour is dispatched, how long it would take. So we just use times equal to distance divided by speed. Distance is 135.57. Time is speed is 200. So the time you will get is around 0.678 hours. So yeah, in word problems, you just want to translate this into something similar to this, which is we have a triangle. We know a few lengths. We know a few angles. We know a few lengths, and see what lengths and angles you would want to find. Okay. So here's another question. So I would give, it's pretty similar to the previous question. So using this information provided in the diagram, we want to find the height of the pyramid, which is this one right here. So have a try at this question. I will give you around 3 minutes or 5 minutes ish. So yeah. So I will give you a quick hint on this question. So a nice way to think about this is to use some algebra. Let me see if I could. So we know there's this weird thing right here. So we don't know the whole length of this. We don't know this whole length here over here. We only know the length is this one particularly weird point over here. So what we could do is we could let this length here be x and let the height over here be h. So then you can get a system of two equations using something like tangent. This is not even law of sines, actually. Wait. Yeah, because we have a right angle. So this is one way you can think about this. Let me think there's another way. Another way you can think about this that uses law of sines is you can find this angle and consider this triangle over here. This angle is calculatable. We have this situation, we know this angle, we know this angle. So therefore, this angle is just angle 1 minus angle 2. So right here, we know this angle and we know this length. This length is 200 minus 100. So this length right here would be 100. So therefore, once we know this, we can deduce these two guys and like a whole bunch of other important lengths that could be eventually used to find h through other right triangles. So yeah, that's a quick hint. There are two potential ways you can do this. So yeah, continue having a try at this question. I just realized that previously my microphone was sensitive. My microphone sensitivity was really low. So I hope you can hear me better than you heard me before. All right. So now assuming you had a try at this question, I would first go on to present the solution using this as x and this as h, and solving a system of two equations. So right now we know that if you consider using this angle right here, we can use that the tangent of 46.27 degrees is equal to h over x plus 100. Tangent of the other angle, 40.3, this angle, we would be h over this entire base over here, which is x over here plus 200. So this would be h over x plus 200. So now we could, let's see, rewrite the first equation. Let me see if I can practice over here. We can rewrite the first equation so that we can isolate the x. So x plus 100 is equal to h over the tangent of 46.27 degrees. Over here, we have x plus 200 is equal to h over tangent of 40.3 degrees. Now, this is extremely useful. This looks like a 9. Now, this is extremely useful because we could set the two x values together. What I mean by this is the first equation, we get that x is equal to h over tangent of 46.27 degrees minus 100. And from the second equation, we get that x is equal to h over tangent of 40.3 degrees minus 200. A common trope is to like we have two different ways to compute one variable. So we know that because that one variable is a constant, we know that these two ways to compute this one variable must be the same. So therefore, we get that h, I'll use cotangent. This minus 100 is equal to h times cotangent of 40.3 degrees minus 200. So yeah, it just remains to solve h. You can solve h using any standard way. It's equal to 100 over cotangent of 40.3 degrees minus cotangent of 46.27 degrees. This is approximately 449.2. So this would be one way to solve this question. Another way to solve this question, let's see. I'm just gonna. Another way to solve this question would be the law of sines method. So we already have this, right? This triangle situation. We know this bottom length is 100. We know this angle. We know this angle. So this angle right over here. For reference, this triangle, I'm just redrawing this one over here, this little slim triangle on the very left. So this angle right here would be 46.27 minus 40.3. This right here would be equal to 5.97 degrees, I think. So we can now apply a law of sines because let's just call this guy right here D. We know 100 over sine of this angle right here, 5.97 degrees, is equal to D over, or maybe not. Let's not let this be D. I'll let this length right over here be D. So it will be equal to D over the sine of this angle right over here, which is 40.3 degrees. And then you can solve for D. D is equal to 100 sine of 40.3 degrees over the sine of 5.97 degrees. And then we could apply basic trigonometry because we know this right here, that is D. This right here, this right here, that is D. And we know this angle. So we just apply basic trigonometry to find this one. So therefore H would be what? So let's see. It's sine of 40.3 degrees times D. And you could compute this and I'm not going to do that. You could just plug it into a calculator. You get 449.2. So a tip when using calculators to solve questions would be that you always want to plug in the final result. What I mean by this is suppose you have gotten that D is equal to 100 sine of 40.3 degrees over sine of 5.97 degrees. Suppose this, I don't know what this is. Let me see. One sec. Let me see. Oh wait, this is not 40.3, my bad. It's this angle. It's actually 46.27. I think this should be. Yeah. So suppose you figure out that this angle, right? So D is approximately 621.867096729. And suppose that's what the calculator gives you. So to find H, we'll need to multiply this number by sine of 46.27. So usually to avoid, so if you just were to type out 621.867 times sine of 400, sine of 46 times 27 degrees, there is a high potential for it to not provide a precise answer up to 3 significant digits, which is required for if you're taking AP Precalculus and stuff. So the idea is to either store this in a variable if your calculator is advanced enough, or just type out the final expression into the calculator directly. And in that part, I'll find that yeah. Okay. So the next slide would be, so we've covered the law of sines. There's actually a law of cosines and actually a law of tangents, but no one has like, that is completely useless. I've never seen the law of tangents used, but the law of cosines is really important and you should definitely know this one. So what this theorem is saying is that when we have an A here, you have a B here, and you have this angle C, then we can actually find the length of this opposite side. It turns out to obey something like this. C squared is equal to A squared plus B squared minus 2AB times cosine of C. So this one might be slightly more difficult to memorize, but if you were to use this enough times, you would definitely memorize this. Sometimes you would see it in this form when you want to find, when we know all three side lengths and we want to find the angle, you would use cosine of C is equal to A squared plus B squared minus C squared over 2AB. What I did was I simply just solved for cosine of C. I moved this to the left-hand side and C to the right-hand side, and I divided by 2AB. So the proof of the law of cosines. Okay. Let me see. So the law of cosines proof could be split up like this. The knowledge of the proof is not strictly required, but I find it a really nice practice when it comes to trigonometry. So we know this is A, this right here is B, and this right here is C. We want to find this guy, and we also know that this is angle C. So the idea is to draw this height over here for two reasons. One, well, for the most important reason is to compute C, an extremely powerful tool that we already know, have already proven, is the Pythagorean theorem. So using the Pythagorean theorem, we can actually, if we were to find, let me use a different color, this guy and this guy, and when we use the Pythagorean theorem, then we can potentially find C. And another indicator for this is that we actually have a C squared. So yeah, if you know the Pythagorean theorem, C squared is equal to this squared plus that squared. So this is a particularly nice sign. So how would you find something like this? Well, the height, well, if you notice looking at this right triangle, one sec. Oh. So looking at this right triangle, we can get that the height would be equal to A times cosine of C. And then to find something like this right over here, wait, no, it's not cosine of C. It's sine of C. My bad. And to find this one, we know the whole length, and we also know this length, again, using trigonometry. So let me use a bit of variable. Let me label these points, actually. So we know that CH is equal to A times cosine of C, again, using the same right triangle. And therefore, we get that AH is equal to B minus A times the cosine of C. Okay, so now we can use the Pythagorean theorem. So we know that C squared is equal to H squared plus AH squared, which is equal to, by plugging in these values, A sine C squared plus B minus A cosine C squared. Okay, so let's expand this. Plus B squared minus 2AB cosine C plus A squared cosine squared C, cosine C squared. Look at this term and this term. If you were to combine them, if you were to combine this term and this term, you would get that A squared times sine squared C plus cosine squared C plus B squared minus 2AB cosine C. And this right here cancels out to be 1. So what is this? This is A squared plus B squared minus 2AB cosine C. And compare it with this formula, and we see that it matches. So the proof behind the law of cosines is just Pythagorean theorem. So a thing I wanted to point out when looking through the proof of this law of cosines is that what the idea of behind what we did is that we just looked at something. So we looked at the side length that we wanted to compute, and we asked ourselves, okay, so to compute the side lengths with the tools we have available, what are some potential candidates for other lengths that we have to compute first? Because sometimes the length that you want to compute cannot be computed in one step. It has to be computed in multiple steps. For instance, to compute the length of AB, which is just C, you need to first compute BH and AH. In high school math, you would almost never need to draw any auxiliary lines. So in most problems, it will provide the lines for you. So you just need to look at which side lengths you want to compute and where to compute the one you need. So yeah, that's the idea behind that. All right, so we got a really basic application of it. We want to find AC squared. We know AB, we know BC, we know their angle between AB and BC. And we just use law of cosine. So I would let you do this, plug in the values and see if you understand the law of cosines. And yeah, feel free to send me the answer if you got it. Oh, and wait, sorry about that. Oh, for this one, I was actually wrong about this answer. For the calculator, it's not 449.2. It is actually 449.3. 364. So yeah, it does not affect anything else beyond the last step. So I will scroll back down. So continue having a try at this question. Okay, so assuming that most of you had sufficient time to at least think through this question. So through a direct application of law of sines, which, as let's recall it again, is c squared is equal to a squared plus b squared minus 2ab times cosine of angle C. The C in this case is actually angle B. Oh wait, I forgot to mention that the C squared can actually be any of A and B. I hope that was kind of obvious, but if it isn't, we also have A squared is equal to B squared plus C squared minus 2BC cosine A, and the same thing for B and blah blah. So in this case right here, we know that angle B is 30 degrees. So applying law of cosines, you get 7 squared plus 9 squared minus 2 times 7 times 9 times cosine of 30 degrees. So that is equal to AC squared. So let's compute this. 49 plus 81, that's 130. And then minus, let's see, that's 126 times root 3 over 2. So that would be 130 minus 63 root 3. And because we want to find AC squared, we just compute this, which turns out to be 20.881, I think. Yeah. So does anyone have any questions on law of sine, law of cosines in general? Okay, so if there are no questions, I'm just going to, because you're doing really well in time, I don't want to end up in the situation like last time in which we had more than enough time. I'm going to go ahead and give a 5-minute break. You could spend the time to review the law of sines and law of cosines if you want. And yeah, so let's just take a 5 minutes break real quick. All right, so let's get back to it, I guess. So yeah, so where was I before? All right. So law of cosines. Oh yeah, so in this case right here is the other case I was mentioning about. Wait, this is a quicker. Oh, this is a quicker button. Okay, so the cosine c, which is equal to a squared plus b squared minus c squared over 2ab. Of course, you could just easily derive this using this formula. I just found memorizing this formula also sometimes really quick and efficient. Now, so if you really feel like you have too much formulas to remember and stuff, well then, yeah, it's not too hard to derive. But so the idea behind this is again cosine of angle BAC using law of cosines is equal to, let me see, this ABAC BC. So this is 8, 15, 13. So it's equal to 8 squared plus 15, 8 squared plus 15 squared minus 13 squared over 2 times 8 times 15. What is this equal to? On the top, we have 64 plus 2. Oh, that's 289. 289, 169. That's 120. And the bottom is 240, I think. So this right here is half. Oh, so this is actually a special angle. So angle BAC is just equal to the angle that makes cosine of theta equal to half, which is just 60 degrees. Of course, if this was a uglier fraction, you would just write arc cosine or cosine inverse of the uglier thing. But in this case, it turns out nice, so we don't need to do that. So that's something. Okay, so of course, let's finish off law of cosines with a application question. So in this one here, we have two boats move away from each other at 6 miles and 11 miles per hour, respectively. And in the beginning, of course, they started together. So they face, so one of them is pointing this direction, the other is pointing another direction that is 60 degrees apart. So they move apart for 2 hours. And we want to know how far these two boats are. So distance is equal to speed times time. So speed is equal to 6. After 2 hours, this boat number 1 would have went 12 miles. Boat number 2, 11 miles per hour. After 2 hours, 22 miles. So let's call that A. Let's call this B. Let's call this C. So using law of cosines, we can get that the distance BC squared is equal to 12 squared plus 22 squared minus 2 times 12 times 22 times cosine of 60 degrees. So this right here is equal to 144. 264. I think this is equal to 364. So BC would be equal to twice of root 91. Yeah, I think this is right. So if you were to round this to, this is 19.079 miles. So yeah, law of cosines and application. That's around how to use law of cosines. Okay, so the last thing you would want to know is Heron's formula, which looks slightly different from the rest. So, okay, so in geometry, there's a convention, of course, to name S as the semiperimeter of a triangle. So S would be equal to A plus B plus C over 2. That is just semi-perimeter. It's semi of the perimeter, which is A plus B plus C. So we know through Heron's formula that the area of the triangle with side lengths ABC is given by this root of S times S minus A, S minus B times S minus C. It's actually really symmetrical inside. So yeah. So this is typically used when we know all side lengths and have no angles. Of course, you could derive the angles through something like law of cosines, but this is just a really convenient way to calculate the area of a triangle without any angles being known. So I would quickly prove this real quick. Let's see. The proof of this theorem, I think, could be slightly more nuanced. Let's see. Again, I think the proof of this theorem is something that it's just really nice to like know in general because it helps you with solving geometry using trig in general. Okay, so we have a triangle ABC. There are a lot of ways we know currently to compute this triangle ABC. So one way would be, of course, to take a height like we did for law of cosines, for the proof of law of cosines. Another way would be to use area is equal to, oh, I already used A. I'll just write area is equal to half times AB sine angle C. So this formula, it's actually surprisingly really important in geometry. The proof behind this is somewhat similar to law of cosines. You can try to prove this after class, but again, you could prove this using, again, like you could just do this. It's actually way easier than law of cosines, the proof of law of cosines. So we have this angle. You want to find this one. You know this one. This one here, we can use the right angle, the right triangle over here, and you could derive the area using these two side lengths and this angle. So that is what I'm going to be using, although it is also possible to prove Heron's formula by taking a height. So, all right, so this is going to get a little bit messy. So first things first, the area of this triangle is a expression. It's just like an expression with a huge radical above it. So it makes sense to prove that area squared is equal to a fourth times a squared b squared sine squared c. Another advantage of this is the sine squared c part. So look at the sine squared c. We know sine squared c is equal to 1 minus cosine squared c. Let me see if I have this. Yeah. Okay. So cosine squared c, by the law of cosines, we could compute cosine squared c using law of cosines because we, in this case, we only know the three side lengths. Okay. So without further ado, let's get into this. So we have cosine squared c is equal to, by law of cosines, a squared plus b squared minus 2ab times cosine of c over 2ab. And then, well, I thought I had this on fixed. Whatever. Okay, so then we just plug that in. That's not particularly fun. Okay, so let's see here. Let's expand this actually. So let's see. We have 1/4 of I'm thinking of this on the top of my head. Yeah, I think expanding it works. Oh wait, what am I doing? Wait, I just realized I don't know what I was writing here. My brain isn't thinking properly. Wait, that was kind of embarrassing. Wait, this is a squared plus b squared minus c squared. I don't know why I wrote 2ab cosine of c. So it's equal to this. Yeah, I was wondering how to get rid of the cosine. And I was like, yeah, that's my bad. Okay, so this, yeah, this makes far more sense. All right. So now we can expand this for 1/4 of a squared b squared minus 1/8 times ab times a squared plus b squared minus c squared. What I have done is I just basically distributed 1/4 of a squared b squared, first the one, and then to this fraction over there. When I distribute it to the fraction, the one of the ab's cancel out with the ab on the bottom, and I merge the two with the 4. So it's 1/8 times ab, which is what's left of that. And then there's still a numerator, which remains untouched. Okay. So now let's expand this completely. This is 1/4 times a squared b squared minus, wait, am I doing this right? I think I am. One second. I need to check this real quick. Did I miss something? Oh, wait. Yeah, I'm being dumb again. I was just cosine c is equal to the bottom expression in the inside. Cosine c squared is equal to this expression squared. So yeah, oh, I'm being not too productive today. Okay, let me see. Uh, oh my God. 1 sec. Why is it like a shit block? Okay, there we go. That's nice. And the particularly nice thing about this actually is that, oops, is that the ABs on the bottom actually cancel out completely now, actually, because we have an A squared, B squared. So we still distribute it. And we realize that because on the bottom here, we have a 2AB squared, it actually cancels out. So what we are left with is actually 1/16 times A squared plus B squared minus C squared. And here it gets really messy. So we will expand this real quick. I think this is right. Yeah, I think this is right this time. So if you were to expand this is now just an algebra question. We converted all the angles and trigonometry into, what am I doing here? We converted all the angles and trigonometry into just basic variables that we know how to handle. So if you expand it, you will get this. And then we could continue our absolutely horrendous grind of this. So we have, you know what? I'll just isolate the 1/16. I don't want to write that like a lot of times. So we get 4 squared, 4 times a squared plus b squared minus a to the 4th minus b to the 4th minus c to the 4th minus 2a squared b squared plus 2b squared c squared plus 2c squared a squared. Now what? So let's combine those annoying what we're doing next is we're going to combine this guy right over here with this guy because that is duplicated. Oh, okay. So this is equal to 1 over 16 times 2 negative of a to the fourth minus b to the fourth minus c to the fourth plus 2a squared b squared plus 2b squared c squared plus 2c squared a squared. Okay, so now there are two potential ways. So if there are two potential ways to
Oh, Samuel, we cannot hear you anymore. Uh...
Okay, I guess I'm gonna do the rest of this. Okay. Uh, so Samuel left. Samuel left off here. Let's see. Oh, okay. Uh, yeah. You're at that stage. You're just trying to simplify it now, right? Like from the bottom. Right. Um, okay. Let's see. Do I remember how to? Oh, wait, actually. Okay. So we want to simplify this. Plug in. Wait, Samuel, what are you going for here? Factor it? Alright. Okay. So if we say that if we say that A is equal to B is equal to C, um, what? Uh, okay, wait. Oh yeah, okay, yeah, that's fine. Um, so if we have, or we're actually just trying to prove herons, so it's okay if we use the formula that they've already given us, which is square root of s minus a b s minus c. So if we expand this, that's s minus a is, or s is a plus b plus c over 2. S minus A is negative A plus B plus C over 2. S minus B is A minus B plus C over 2. S minus C is A plus B minus C over 2. That's kind of inconvenient, but we can use difference of squares. I'll show how. Let me erase this. So yeah. This part is if these two multiply together. Oh, okay. These two multiplied together is equal to b plus c over 2 squared. Um, what? Is equal to b squared plus c plus c squared over 2. Um, minus. Oh, actually over 4. My bad. Over 4 minus. I hope I'm doing this correctly. Yeah, that seems correct. The product of these two is, well, the difference term is b minus c. So you have times a, oh, shoot, uh, times a squared over 4 minus b squared minus 2bc plus c squared over 4. So once you multiply those two, or once you expand those two, actually, you're gonna have, let me write this out. B squared, oh my god, b squared plus 2bc plus c squared minus a squared over 4 times a squared plus 2bc minus b squared minus c squared over 4. Factor out the 1 over 16, which we have here. And if you expand that, I can do it term for term. B squared and a squared, they will have two copies. So which is b squared and the a squared here. And okay, let me erase the denominators here. And the b squared, okay, wait, no. So b squared and a, yeah. Starting from b squared, you have b squared and a squared, and negative a squared and negative b squared, which is the same as this 2a squared b squared term. Also erase the bottom of the thing. Okay. And then and then for b squared c squared, you have uh wait, okay. It's like the next one you have is 2 2b cubed c, and then this is canceled out with this. Next is negative b to the fourth in these two, which is this. Next is negative b squared c squared. Wait. Okay, this is not good. Let me check something real quick. Um, my bad. Give me a minute. Uh,
Yeah, I think
Wait,
it's
okay.
actually easier to factor it directly.
Yeah,
But
it might be easier to factor directly. Wait,
okay.
I actually don't know what I did wrong. Did I do a sign error? I probably did a sign error. Okay, that's fine. Wait, okay. Actually, factoring is probably much better for this problem. I'm pretty sure. Um, okay, so this thing we know that one of the factors is a plus b plus c. So like so if we can set a is equal to negative b minus c and see if it works, and it does work. So yeah. Um.
Wait, that is way beyond the scope. So let's just not do that. Because
Yeah. Wait.
multivariable
Where you find the
factoring is
height.
really.
Just use the method where you find the height.
Yeah, but then we already continued so far into this method. It's not exactly best to abandon it. But it shows you a really powerful application of power of difference of squares, I think. Check this out. So I've realized that I've been really dumb and I should have recognized the difference of squares right over here. So plus c squared. So what I've done is you rewrite this in terms of a difference of squares. This is a square. This is also a square. This is a difference of squares. And remember, like, if you were to look at the final formula, you could what Vincent had been doing the entire time is expanding out this factor thing. Okay. These two. Wait 1 sec. I'll make this look more aesthetic. So, all right. So now we have these two expressions over here. This one and this one. The first, I forgot to turn on my video. I think that's fine. So the first right here would be equal to a plus b squared minus c squared. Why? You look at this guy right here. That is a plus b squared. Look at the second factor. This is negative of a plus b squared. So therefore, you get c squared minus a
It's
plus b.
negative of a minus b squared.
Huh?
The second one, it's the negative of a minus b squared.
Yeah, exactly. So because if it was a plus, that'd be really bad because now I can't even use difference of squares anymore. Here's the idea: is I want to use difference of squares twice. Now the second time I use it, that's what splits it into 4 different factors. So we have a plus b. Oh wait, a plus b. Oh wait, you're right. You're right. Oh, that's what you mean. Oh wait, my bad. Oh. Let me see. That's not good. Let me see how I can get rid of. Yeah, thank you for pointing that out. Wow. Okay. Yeah, I think this. I don't know if this is right. I'll just work it out and see if this is right. So a plus b minus
Yeah, it
c
is.
times c minus a plus b times c plus a minus b. And now you look at the 1 over 16 and you distribute it across each of these guys. And let me just write it over here. This is equal to 1 over 6. This is equal to a plus b plus c over 2 times a plus b minus c over 2, c minus a plus b over 2 times c plus a minus b over 2. So this is equal to, this right here is s. That right here, it's equal to s minus c. Why? Because S minus C is A plus B plus C over 2 minus C. And if you write C as 2C over 2, this is A plus B minus C over 2. So this right here becomes S times S minus C. And doing something similar, that is S minus A. That is S minus B. So yeah, that if you were to compare it, because this is area squared, to find area alone, we would just take a square root. All right, so yeah, so maybe it would be easier if I used height. Not exactly sure, I think. But then either way, you cannot escape this, whatever this horrendous thing is.
Yeah,
And then, yeah,
like either
so
way, it's a difference of squares, Bash.
yeah, so the difference of squares part. So a lot of this is more is definitely not. You definitely don't need to understand every step and understand why it's going, what exactly is going on. You just need to, because in AP pre-calc and stuff, all you need to know is the formula. So what I want you to take away is not this. This is here is something fun that you could work with, but is way beyond the scope of pre-calc. So what you should concern yourselves with is how do we compute area of a triangle? There are actually a lot of ways you can compute the height and the base. You can use half of AB sine C, and now you know Heron's formula. So the idea behind this is we want to find sine C, and to find sine C, we want to find cosine C, and to find cosine C, we have law of cosines to help us. So yeah, that is that. And if you were to expand it, I'm pretty sure that you will still get the same thing anyways. This is a really classic example. Let me see if Vincent wants to take it from here, because I think I've been talking way too much. Actually, yeah, there's only 6 minutes left. Let's just not. Let's just finish this class. So, I'll do this one real quick. That other one, I'll just. So let's just do this one first, because this one gives a more ugly answer, and I like that. So, using Heron's formula, this right here would be equal to. So first, we'll compute the semi-perimeter. This is 4 plus 9 plus 6 over 2. This is equal to 19 over 2. This is, yeah, not the best looking triangle. So 19 over 2 times, let's see, that minus 4, which is 11 over 2, times half times 7 over 2. Let's see what that is. That is equal to, root 1463 over 4, I think. Yeah. So in this right here, you could chug into your calculator. Let me check that into your calculator real quick. Should be around 9.562. So this last example here, I will leave you guys to think about this for around 2 minutes. The answer to this question, in case you want to know, is actually an integer. That's what makes this one really good. This is a 13, 14, 15 triangle, and the area is actually an integer. So try to use Heron's formula on this one. And if you get what that integer answer is, please send it to me in the chat. Yeah, so I see that a lot of you have gotten it. This one is a really nice one. And yeah, if you have sent me an answer with the using the purple Samuel Lee, I don't check that one. I just use it's sort of like an iPad. I just use that one just to write on the screen. So if you sent any message to me using the purple Samuel Lee, then if I didn't respond, yeah, I'm sorry about that because I did not check that one because I've been writing on the screen with that one. Okay, so yeah, the answer to this one is really nice. S is equal to 21. Plug it in. 21 times 8 times 7 times 6. Ooh, this is equal to square root of 21 times 48. Nope. Times 8 times 48. No, times 42. That is twice of 21. And we are left with the 16. So that's 42. So yeah. So yeah, that's about it for trigonometry in geometry, and also concludes me and Vincent's 2 weeks of teaching trigonometry in both algebra and geometry. So I hope, so first, is there any questions that you would like me or Vincent to answer? So is there anything that you would like us to go over and review?
Yeah, I think that's good then.
Yeah, so if you guys have no questions, then let's just call it a day. So
Yeah, thank you all for coming to class. Yeah.
So yeah, so thank you all for attending our 2 weeks of teaching pre-calc. I hope you've all learned something. And yeah, have a great rest of your summer and rest of learning pre-calc. Thank you all for attending.
Yeah, thank you all.
Sarah, it's not done for pre-calc is not done. It's just we teaching. So the next 2 weeks will be different pair teaching.
Our next two classes.
Yeah, next 2 classes. Yeah.
Yeah,
Vision.
but we still have one office hour.
Yeah,
Yeah,
there's
one office.
Yeah, one office hour. Yeah. Okay. Okay. Bye.
Bye everyone.
thank you all. Bye.
Bye.